How do we explain a long-range force, such as gravity? How can things possibly interact over great distances without touching? This is one of the great historical mysteries of physics, and it goes back at least as far as Isaac Newton. Although Newton was the first person to discover a mathematical way to predict how objects would move under the influence of gravity, he admitted that he could not explain how it all worked, how two things could interact without touching. He could not explain this so-called action at a distance. The answer, the explanation for action at a distance, came 100 years later. It was Pierre-Simon Laplace, a French scientist and mathematician, who first hit upon the idea of a gravitational field. Laplace proposed that every object creates its own gravitational field, a sort of personal, self-generated force field that extends through all surrounding space all the way to infinity. Your body creates its own gravitational field, but it's much too weak to be noticed. But an enormous collection of matter, like the planet Earth, generates a strong gravitational field that we interact with very noticeably every moment of every day. The gravitational field of the Earth is always present wherever you are. It extends all the way out to infinity. And so you are always interacting with the field. You are always touching the field, in a sense. The moon out here, although it's not touching the Earth, is touching the field. It's in contact with the field, interacting with the field. So Laplace solved the problem of action at a distance by saying that there is no action at a distance. When you experience a gravitational force, you are interacting with the gravitational field, a field that is created by something possibly very far away, the bulk of the Earth, but is always present right at the location where you are, wherever you are. Let's zoom in and take a look at the gravitational field near the surface of the Earth. Here we've got all of these radiating lines pointing inward toward the center of the Earth. What do they look like if we get really close to the surface? And we'll discuss the concept of a gravitational field as a vector field. Visualizing the gravitational field of the Earth near the surface of the Earth, we can draw like one of two types of diagrams to visualize it. This is a so-called field line diagram. Here are those same lines, those same rays radiating outward from the surface of the Earth. They're actually pointing inward toward the center of the Earth. If we zoom in close to the surface, those rays are just going to look like parallel lines, equally spaced, indicating the uniform strength of the gravitational field near the surface of the Earth. Another way of visualizing it is with a so-called vector field diagram, where at every point in space, we draw a vector that represents the gravitational field. Yes, indeed, gravitational field is a vector. And uniform, meaning it has the exact same magnitude and direction at every point in space, as long as we stay near the surface of the Earth here. So we said that the gravitational field has a certain strength. Your body creates its own gravitational field, but your field is very weak. So how strong is the field created by the Earth? How do you measure the strength of the field? At every point in space, the field has a strength that we call little g. As long as we stay near the surface of the Earth, the strength is pretty constant. But the field also has a direction. It points toward the thing that creates it. So at every point in space, we define the gravitational field as a vector, g, with a magnitude or strength, little g, and a direction that is always down toward the center of the Earth. You may have guessed that this little g that represents the strength of the gravitational field is the same little g that you have already encountered in free fall. You know that objects in free fall accelerate downwards at a rate of about 9.8 meters per second squared. This value, the so-called acceleration due to gravity, is exactly what we mean by the strength of the gravitational field. So the strength of the gravitational field near the surface of the Earth is 9.8 meters per second squared. But we usually express the field's strength using a different unit, not meters per second squared. We've already found from Newton's second law that a meter per second squared is equivalent to a Newton per kilogram. So actually, we always express gravitational field strength in newtons per kilogram instead of meters per second squared. They're equivalent. the gravitational field is the same strength everywhere as long as we stay near the surface of the Earth, but yet different objects experience different gravitational forces. Here near the surface of the Earth, we have a giant ground sloth and a sheep, and this giant ground sloth is pulled harder by gravity than the sheep is, even though they are both interacting with the exact same gravitational field. Little g is the same, gravitational field is the same here as it is here, but two different forces. So there must exist some property that all matter possesses that tells you how strongly a given object is going to interact with the gravitational field, how strongly it's going to be pulled by gravity. And that's a familiar property. Of course, we call it mass. The more mass an object has, the greater the gravitational force it will experience when you put the object into a gravitational field. So we're about ready to write down a mathematical model for the force of gravity on an object of mass m interacting with gravitational field g. The magnitude of the force depends on two quantities. It increases as mass increases, and it also increases as little g, the magnitude of the gravitational field, increases. If you were to go, say, to a lower gravity planet, such as Mars here, there the strength of the gravitational field on Mars, little g, is about 3.7 newtons per kilogram, as compared to 9.8 newtons per kilogram near the surface of the Earth. So that's about 40% the value at the surface of the Earth. You take that same sheep and transport it to Mars, put it in a smaller gravitational field, it's going to feel a smaller gravitational force. The sheep has the same mass, but in a weaker gravitational field, it experiences a weaker gravitational force. Hence the proportionality to the strength of the field, to little g. Okay, therefore, since the force is directly proportional to these two quantities, and points in the same direction as little g, we can now state the law of gravity as it applies to the surface of the Earth. It applies near the surface of the Earth or the surface of any planet. The force of gravity on an object of mass m located in gravitational field little g can be found just by the product of the mass and the gravitational field. Note that this is the mass of the object, such as the sheep here, whereas little g is the gravitational field produced by other masses, namely the Earth. The Earth is producing the gravitational field. The sheep of mass m is just sitting in the gravitational field, and that product gives us the gravitational force on that sheep right there. So we call this the law of gravity as it applies near the surface of the Earth. We'll discover a more general universal law of gravity later on. From this equation, by the way, we can see why the gravitational field strength, little g, is usually measured in units of newtons per kilogram. If the force is in newtons and the mass is in kilograms, then g here must have units of newtons per kilogram for kilograms to cancel out, so we have newtons equals.